the rational number 3/2 as your eta sequence. So it just went 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. If you just alternate the forking 1, 2, 1, 2, it gets very, very complex, and up the right-hand edge of the tree, you get numbers that are basically 3/2. If you want, the next number, a sub n plus 1, is equal to 3/2 times a sub n floor of plus 1. And that 3/2 thing throws chaos into the world a great deal. It's a little bit like the 3n plus 1 problem, because it involves multiplying by 3 and dividing by 2. And it turns out it's a very, very difficult problem, and I was not able to, even for the simple eta sequence, as I say, of 1, 2, 1, 2, 1, 2 as the fork function for the tree, it was too hard. But I played around with all sorts of trees, and I thought I'd show you one that I did not play around with, but that I could have invented, but I wouldn't have been as imaginative or as silly as to invent this particular tree. This is a tree where above any integer you put, let's take one right here, 2. You put that many, you branch it out that many times, 1 and then 2. And here 3, you go 1, 2, 3. Except when you're on the right-hand side, and that's why I put these things with little suns or rays coming out of them. When you're on the right-hand side, you don't go 1, 2, 3, 4, 5, you go 1, 2, 3, 4, 6, for some crazy reason. Now, as I said, I would never have thought of anything that silly. But here it is. 1 goes to 1, 3 goes to 1, 2, not 3 because we're on the right-hand side, 1, 2, 4. Or 2, because we're on the right-hand side, does not go to 1, 2, but to 1, 3, and so forth. This is a funny tree, but as I say, I could have invented this one, but I did not. Anyway, I was very interested in these trees, but I was also playing the function game, and one day, only a few days after I invented the g and the h function, I came up with this, and I was flattered that Neil chose to talk about this, but I suspect he partly did it because he was at the conference. But it was very nice to see it be mentioned, and indeed it's a sequence that has very chaotic behavior. I explored this. This is, as Neil pointed out, if you want to know what the next term is, here after this one you take 10 and 9, those are the last two terms, and you go back, count back 9 and 10 terms, you find two numbers and you add them and you get 11, and that's how it extends. But as you can see, it starts out looking as if it's monotonic, but it isn't. It goes down. It starts getting crazier and crazier. Here is a graph of the first, 100 values, or I can't read the bottom, 120 values. And you can see that, that it has little plateaus of stability that get longer and longer and longer about every, sort of doubling each time, twice as far out. And I thought that was going to be a reliable fact, but it turns out to break down after a while. This is showing those, here we are seeing those things in red that we saw before, these plateaus of stability, but that was the last one there. I mean, it's sort of constant here, but it's not of the predicted length. And after that, it just sort of hovers around, kind of constant, but not. And then it explodes. That's the place where it's kind of constant, but it's not really constant. And then it has a huge explosion. So this is what it looks like going out to, what is that, 10,000? And going out to 100 million. And it is still, as Neil pointed out, an open question. Does it exist for all n? Nobody has proven, as far as I know, anything about it. Now, there were, of course, the question came of generalizing it, and one kind of generalization was replacing the 2 by the 4 and having the initial values be 1, and that turned out to have an interesting graph. It increases always either by 1 or 0, and so if you take the block length, that is, how long does it stay constant, or let's see, am I saying this right? I think I'm saying it right, yeah, how long does it stay constant? You get this sequence 4, 1, 1, 2, 2, 1, 2, 2, 1, 3, 2, blah, blah. And this sequence consists of 1s, 2s, and 3s, except for the 4 at the beginning. And there is, I guess these are called morphisms that give you a block from terms 40 to 80, then from terms 80 to 160 by using these substitution rules. So this was kind of interesting because here was a very close cousin to the original function, the Q function, which were completely explicable. It was a completely regular and predictable kind of behavior, whereas the Q function seemed to have just crazy behavior. And that still is something that people have not really come to terms with. There are a lot of people at the University of Toronto who have explored it. Steve Tanney and some of his, many of his graduate students and postdocs have explored it, but nobody has been able to explain the behavior. So this is the sort of the generalization where R and S are now arbitrary integers, and you can have different initial conditions, and in fact it's very interesting to explore different initial conditions, but if you just set them all to 1, that's already interesting enough. Here, for example, if we take 2 and 4, this is what you get. I think my next graph may show, I don't remember what it is, but it may show what you get with different initial conditions. Yeah, 1, 2, 3, 4. Got a lot of points that it's got to put up there. It looks quite different because that one just was like one big funnel, and this one looks like the Q function that we had seen before, so somewhat at least. So these are very mysterious functions that nobody yet has totally analyzed. What about for other values? Well, this is a natural thing to explore. With Greg Huber, a friend and colleague, we explored these things quite a lot and found that, as it says here, Q dies at age 55. And we don't know when John Conway will die, but we do know when Q dies. This Q, 2-3, it dies at age 55. And the general question is, well, here is what it does, and if you plotted the line, of y equals x, it would go like this, and this point here is just a little above it, and that's what makes it die. And so this is the life story of Q23 with initial conditions 1 and 1 and 1. Here's another one, the life story of Q16. It dies at age 2355. And so the general question is, which ones die and which ones live? And here is a table. I'm sorry, it's not very graphically elegant, but anyway, the question marks represent what look like, for all appearances, for all we know, infinities. As far as we can tell, the question marks, these 3 question marks, are infinities, and all the others are mortal. And so you might ask yourself, what is this row here? Let's imagine that we hold R constant and let S vary, and look down this row, or look down the second row. And I'm just going to show you, if I plot both of those 2 rows together, what I get. This is the lifetime. This is the death date, if you wish, of with 1 comma s. So 1 is the first parameter, and s is a variable. This is the s-axis, and it looks like, again, one of these strange funnels, but it has kind of streaks inside it. And this is 2s, and it again has the streaks are much clearer here. And I'm blowing up the 1 and showing you what it looks like in great detail. And I always zoom in on it, and there it is. It looks, you can sort of see the bands here. If I go back, you can see the bands fairly clearly, but they're not well defined. There's sort of a band there, a band there, a band there, and a band there. And here you can sort of see them. It looks kind of like the Milky Way. If you go to 2s, the bands are far, far more distinct. But if you look at them in detail, they still are extremely weird looking. That's what they look like. I don't know if you can see them well, but they're highly chaotic and strange. even though they form very nice bands, but they're sort of sub-bands and so forth. Very, very complex behavior. We made a conjecture as to which ones are immortal, and they always have to have this form in either R, 2R or R, 4R. For initial conditions 1, 1, 1, almost none of them are immortal, but for initial conditions 1, 2, 3, 4, all of these seem to be immortal. Seem to be. Okay, then this function was another variant that I explored, and it was not as obvious a variant, but it was one that I explored, and it looked something like this, and if you take off the diagonal of the y equals x, subtract the diagonal, it looks like that. And I've called it Conway, as you probably know, because, well, I don't know if I have the newspaper, I guess I didn't put the newspaper article, but in 1988, I was in an airport, and I was reading the New York Times, and I saw that this very functions was the recursive definition was printed in an article in the New York Times. I mean, it's very unusual to see recursive functions talked about in the New York Times, let alone featuring double levels of recursion. And so I was very struck, and I started to write a letter to Conway telling him that I had explored similar things. And then I went to my files, because I was at the airport when I was thinking about this, but when I got home and I was writing my letter, I went to my files, and lo and behold, I found that I had explored this thing many, many years earlier, and had come to understand it. And this was, I had created this tree. This was the tree I had created and it had seemed to have very simple properties. Namely, that. It was the exact thing that I showed you earlier. As I told you, I never would have invented that on my own. But I had invented the function that gave that tree. So I had stumbled across this tree rather than invented it. Anyway, it was a curious coincidence, and I sent the letter to Conway and also to Mallows, and they were. Mallows particularly was very kind. He acknowledged my priority, and even though he had done much more than I had in exploring the nature of this thing. Well, now I come back to the story of G-plot. I'm not going to tell the story, but I will tell you this. I dropped out of math graduate school because these kinds of things, although they fascinated me, didn't fascinate anyone that I was in graduate school in math. Everybody thought it was sort of too passé and too concrete. And so I realized that math was not the career that I was cut out for, and I thought, well, maybe I could do something in physics. And I went and I tried to be a particle physicist for several years. And after several years, I realized that was also not my destiny. It did not agree with me. And in the end, I wound up talking to a solid-state theorist named Gregory Wanier, who told me about a problem that he had that involved things that he referred to as irrational and rational magnetic fields. Now, since I had already studied a lot of number theory and knew a lot about the differences between rationals and irrationals, and it sounded absolutely nonsensical to me to think that there could be any physical difference between rational and irrational values of anything, because nature doesn't know whether a number is rational or irrational. Nature doesn't have room to contain infinitely many decimals. And so I felt there was something attracted me about this idea that there was a problem in physics that seemed to involve rationals and irrationals. And just to make a long story short, I explored the spectrum of this system, and I came up with this structure computationally. And I found that much like my int graph, but in a more complex way, this structure consisted of copies of itself, but distorted, but getting less and less distorted as you go down toward the corner. If you blow this up, you will see it's a very close copy. If you blow this up, it's even more close. If you blow this up, it's even more close, etc., etc. And so this, that led to my discovery of this graph, which has just, this is 1974, and it's just this year, I think it was, or maybe it was last year, been experimentally partly revealed as the spectrum of the situation involved, which is a crystal in a magnetic field. Now, the last phase that I'm going to just mention very briefly of my passion of integer sequences is that when I went on to, I dropped out of physics after getting my PhD, realizing that I was not cut out to be a physicist of any sort, and I got involved in cognitive science. And in cognitive science, my goal was to understand how, I don't know how creativity works, you might say, but I had to find a domain, and I decided that the domain would be the exploration of the structure of integer sequences. And however, I quickly realized that integer sequences, as if you consider them in their full richness, in their full mathematical glory, are far too rich for me to model, for me to try to make a computer model of that process. So I simplified it drastically and came down with a project of finding sequences that would basically, basically involve very, very simple properties of integers. And I'm going to let you try to extend this sequence yourself in your heads. What is the most plausible extension? You don't have to say it, just think to yourself. And now I'll show you the next term. Okay, this is not 21, this is 2 and then 1. Okay, now that you know those two terms, what is the most likely continuation of this? Knowing that negative numbers are disallowed from the domain. And even 0 is disallowed. 0 might be a marginal case. Okay. This is not the eta sequence, this is not triangles between squares, although it might be. So, now maybe some ideas are starting to form in your head. I assume they are. The point is, I'm asking you to go through this mental process because it's this mental process that I wanted my program to go through. I wanted to write a program that would go through a sequence like this, being exposed one term after another and making plausible guesses, modifying its guesses or throwing them out the window, and trying to extend them, not by using brute force techniques, but by using psychologically realistic things, the kinds of things that people would do. Oops. There's another term. Just giving you some time to reflect on what might be going on here. Now you might be saying to yourself, well, it consists of all 2's, except there's a glitch. Perfectly possible. Getting more likely. I think you can get it at this point. And I think you can retrospectively, you can move from right to left, seeing 5, 4, 3, oh, that 2 in the middle there. I can't get it. This one there. That was a trick. It's a different kind of a 2. It's a 2 of a different, it's a horse of a different color. And so this is kind of interesting stuff. It's actually like the beginning of the subsequence of E, 2, 2, 2, 3, 2, 5, 2, 7. So it's a little bit similar to that. However, you look at it and you say, there's a glitch though, at the beginning. What's going on? There's a glitch. And why is it doing this bizarre thing? And of course the answer is there's not a glitch. And so I might, I will say one last thing. You know the simple continued fraction for E starts out, the denominators are 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, and you might think there's a glitch. But actually, you can rewrite it as 1, 0, 1, 1, 2, 1, 1, 4, 1, 1, 6, 1. etc. And even though there's a 0 there, it doesn't hurt anything because it's added to a 1 that follows it. So in fact, it's a totally convergent form. But now the thing is very much like this. Instead of it being 2, 1, 2, it's 1, 0, 1, 1, 2, 1, 1, 4, 1, 1, 6, 1. So that's E in a certain sense. And I called my project Sequence, as we are looking for, trying to identify or characterize the origins or the provenance of integer sequences. So I thought this was an appropriate way to terminate my talk and the conference. Thank you. I shouldn't have spoken so quickly because I guess there could be questions.
Think there are questions?
Yes.
Your com and spelling of the CNS thing reminds me of continued fractions.
Very strongly connected to continued fractions. It's actually very closely related to what in one book are called the closest integer continued fractions. Instead of taking the floor, you take the closest integer, and then you put a plus or a minus after it, depending on whether it's below or above. And you get continued fractions which don't have all plus signs down the diagonal, but sometimes pluses and sometimes minuses. And then basically that's the same. That is a kind. It's essentially the same thing as that. So yes, they're simple continued fractions of a special sort. Exactly. Yes.
So the Markov numbers, phi and root 2, are the numbers whose derivatives, if you take the continued fraction sequences. So does that? I mean, do you study which ones differentiate to things similar to that?
Give themselves back?
Yeah.
Well, yes. Any quadratic number will eventually give itself back, just as in a continued fraction. That is, it doesn't give itself back, but at some point the derivatives become periodic. The count sequence and step sequence become periodic at some point down as you go down, and so all quadratics have that quality. And so if you interchange them, the int of a quadratic is also a quadratic. Now that leads to an interesting and unsolved problem, which is whether int of a cubic number is cubic or int of the algebraic number is algebraic, whether int of a transcendental number is transcendental. Obviously one would think so. But I remember when I was exploring these things, I took just the cube root of 2, generated the first 20 or 30 members of the vertical count sequence and step sequence, interchanged them, and then found a number that had that as its count and step sequence, assuming, hopefully, that it was going to be a cubic number. And then I stuffed it into a whole bunch of, using a computer, I stuffed it into a whole bunch of cubics with low integer coefficients. And I don't know if I should say lo and behold, or no and don't behold, but it didn't solve any of those equations. And that kind of shocked me. I couldn't kind of understand why this wasn't acting like a cubic number, because it seemed very weird for it to for a cubic to turn into a transcendental or into a number of a different algebraic degree, especially given that all quadratics turn into quadratics. So that, and of course all rationals turn into rationals. So I still don't know. That's a good open question. Yes?
I was looking for some notes on this. Did you give talks at Stanford Math Club, which led to some notes called the Ada lore?
Yes.
And is the Ada lore available somewhere that we can...
Handwritten, I think. Or maybe I typed it up at some point. Yeah.
Did anyone ever put it online, or did you put it online?
I did not. I have it in hard copy. I can send it to you. You're right. It was called Ada lore.
A few of us apparently wanted, because Math Overflow couldn't find the answer. So.
Yeah. Okay. If you're interested, just send me an email.
I personally would love to.
Yeah. Just send me an email and I'll get it sent out to you. Just give me your postal address because it's not online.
Right. Yeah.
Oh, I would feel ashamed. I would feel ashamed. Well, you could.
Reference many times in the OAIS.
Oh, is it?
We would be,
I
it would
see.
be okay to put a cached copy on the
Okay.
OAIS.
I guess so. I mean, it's amateurish. dabblings of a teenager, you know, but, you know, okay. I mean, I'm not Galois. Probably, luckily. I wouldn't be here if I were Galois for many reasons.
One of the first paper published by Galois was about the property of quadratic numbers concerning continued fractions. Yes, he found that there was symmetric. There was an influence between the symmetry of the period and the fact that it was a quadratic number.
Interesting. So maybe I am Galois. All right. Is that?
as conjecture, are there any, like the Hofstadter is there, 1, 2, right? The original Hofstadter sequence, when you do the QRS.
Which one? Yeah, 1, 2, with initial conditions 1, 1.
Are there similar Hofstadter-like sequences for which it's provable and never dies?
The only ones, as I said, were 1, 4, where it's completely regular and not, you know, it looks a little irregular, but I mean, it's basically, it's a sequence. I think the term used earlier was an autonomous, was it? Autonomous or something? Sequence where a sort of a morphism gives this. But that's so trivial. It doesn't, you know, I don't mean it's literally trivial, but I mean, compared with the Q sequence, I mean, the Q sequence is just chaotic as hell. I mean, or the Conway sequence, if we want to call it that. That sequence, you know, that one has that very nice, elegant tree. I mean, it's very simple, ultimately. It doesn't have any mysterious properties, you know. So things have been proven, like the Conway one, we know that it lives forever, and we know exactly what it looks like. Incidentally, that scalloped form, that recursively scalloped form, each time when you plot it, it's a discrete thing, because it's just consisting of integers. But if you superimpose them all, if you all scale them all together and superimpose them all, you will get a shape that looks remarkably like something that Jeff Lagarius, is he here today? No? Yeah, there was a graph that you exhibited. It may not really be very similar, but to me, my eye said when I saw that graph, it looked very, very much like the Conway.
The Takagi function.
The what?
The Takagi function.
Is that what you're talking about that you showed? You showed a function that you said was. I can't remember what you said. You said it was nowhere differentiable, but everywhere continuous.
Right. So there's a famous function of this sort called the Takagi function. It was invented by Eiji Takagi in 1904.
Yeah, and I thought it played a role in your talk. Maybe it didn't.
Other talks. In fact, the function for base 2 in that talk is related to the Takagi function. So
yeah, okay.
Closer to what you have there. I was wondering when I saw your slide whether or not that actually was going to be the Takagi function.
Well, that's what I wonder also. That's what I'm saying. If you superimpose, or if you take the limit shape of that Conway function when you subtract off n, the diagonal, will that be that function? I don't know. Anyway, it looks a lot like.
Great question.
Mm-hmm.
The same function comes up in studying the toothpick sequence.
Yeah, that's where it's
Any other questions? Okay, thank you.